In Chapter 16, we deal with compounds that have three bonds to oxygen, carboxylic acids and esters. These compounds are more oxidized than aldehydes and ketones and less oxidized than carbon dioxide. Metabolically, that's important because carboxylic acids are almost always formed as carbon-based molecules like carbohydrates, proteins, or lipids are metabolized for energy. Carboxylic acids and esters are functional groups that contain a carbonyl, that is, a carbon double bound to oxygen. This carbon continues to be the most reactive in the molecule, just like as with aldehydes and ketones, and the carbon of the carbonyl is where we'll see changes happening. Most of these changes in a carboxylic acid change that acid into a functional group that has different electrophilic atoms swapped out for the OH of a carboxylic acid. We call this a carboxylic acid derivative. The OH can be swapped for an OR, an ester, a reaction that we'll talk about this chapter. So we see both the carboxylic acid and the ester highlighted in yellow. The OH can also be swapped out for a nitrogen, which makes an amide, the molecule we see on the far right, which we'll talk about next chapter. Systematic nomenclature is hopefully becoming relatively routine at this point. Naming molecules is really about identifying pieces of the molecules. When we name carboxylic acids, they will be the highest priority group. We will replace the E at the end of a molecule name with oic acid. So just like with alcohols, aldehydes, and ketones, we can have the carboxylic acid listed as the main chain, but also include alkenes or alkynes. On the other hand, we can't have two endings that replace the final E, so we will continue to see alcohols named as side chains instead of with the all ending whenever we have carboxylic acids, just like we saw that for aldehydes and ketones. The carboxylic acids will necessarily be numbered as 1, and we won't need to include the number 1, just like we didn't need to include it with aldehydes. When we name a carboxylic acid, we're just looking for the longest chain of carbons that's connected to that carboxylic acid. And just like with aldehydes, these are actually a little bit easier since you always know that the carbon that you start with is the carbonyl carbon, the one with a double bond to oxygen. So for the molecule in the top left, we start with the rightmost carbon and count 1, 2, 3, 4 carbons. But instead of butane, which would be the name for the 4-carbon alkane, we drop the final E in butane and replace it with oic acid for butanoic acid. If we do have a side chain, we name those side chains before the name of the carboxylic acid and with locators, just like we've done in every other IUPAC naming system. So our 3-carbon carboxylic acid on the top right is a 2-methyl propanoic acid. The next two examples have an alcohol and an ether as side chains. Pause and try to give names for the final carboxylic acids, and go back and look and see what the side chain names are for alcohols or ethers if you can't remember. On the bottom left, we have 3-hydroxypropanoic acid. The alcohol as a side chain is hydroxy. And on the right, we have 3-methoxypropanoic acid. A methyl ether as a side chain in IUPAC form is methoxy. Carboxylic acids, like aldehydes, have common names that don't follow particular rules and need to be memorized individually. However, carboxylic acids and aldehydes have related names. The molecule on the top left, formic acid, is the carboxylic acid version of formaldehyde. Just replace aldehyde with ic acid. The same is true of benzoic acid, which is the carboxylic acid version of benzaldehyde. There are other carboxylic acids that are important to memorize besides those two, though. Carbonic acid, which is the form that carbon dioxide takes when it's dissolved in water, which makes it pretty relevant in our bodies. And the other molecule, acetic acid, is the compound that makes vinegar vinegary. It's also closely related to acetyl-CoA, which is one of the most important biomolecules in our central metabolism. There are many more common names for carboxylic acids than just those 4 common names that we just looked at. Carboxylic acids are some of the first organic compounds that were known, and many of the names relate directly to the substances that they were first isolated from, which you can see in the table. You don't really need to know that, it's just interesting. Carboxylic acids also have informal labels for the carbons based on how far away they are from the carbonyl. The carbonyl carbon itself gets no label, but the first carbon connected to the carbonyl is referred to as the alpha carbon. the beta, gamma, and delta, all following the Greek alphabet. There are 24 letters in the Greek alphabet. We don't generally need to use them all, and we realistically just use the first several letters. No matter how long the carboxylic acid is, though, we'll always call the carbon farthest away from the carboxylic acid the omega carbon, which is the last letter in the Greek alphabet. The lowercase omega looks a little bit like a W, which you can see on the screen. This system of identifying carbons is important in fatty acids, where we identify fatty acids by how far the last double bond is from the omega carbon. For example, an omega-3 fatty acid has a double bond 3 carbons from the end, and an omega-6 fatty acid has a double bond 6 carbons from the end. Carboxylic acids show up all over the place biologically, but are hugely important as components of lipids and proteins, and most of the molecules involving converting lipids, carbohydrates, and proteins into energy. We call those metabolites. Usually these molecules also have another functional group on them as well. We call this a polyfunctional acid then. Biologically, many of these polyfunctional acids are converted in the same way over and over and over again. A common pattern is to do the opposite of a hydrogenation reaction, like we saw in chapter 13. We call that a dehydrogenation reaction. We use that to convert a carboxylic acid into an unsaturated acid. Another way of saying a carboxylic acid that has a double bond. So you can see an unsaturated acid on the left. That unsaturated acid can be hydrated into a hydroxy acid, so that's a carboxylic acid with an alcohol group as well. And that alcohol can be oxidized to a ketone, giving us a keto acid. That's a carboxylic acid that also has a ketone. If you look closely at the diagram on the right, which shows the final steps of the citric acid cycle starting on the bottom and proceeding to the top, the progression is the same on those central 2 carbons. First we have an alkane that dehydrogenates to an alkene. Then we have an alkene that hydrates to an alcohol. That alcohol oxidizes to a ketone. And then eventually that ketone will be condensed and then we'll continue the cycle. The strongest intermolecular force in carboxylic acids are hydrogen bonds from the OH on the carboxylic acid. But without changing molecular size, we also have increased the dipole significantly with the C double bound to another O. When we add stronger interactions without changing the size at all, we make this molecule more polar and more similar to water. This is going to increase the boiling point, and it will also increase the solubility relative to alcohols, which have very similar hydrogen bonding, but much less significant of a dipole. We can compare the boiling points of a few of the straight chain versions of functional groups that we've talked about. We see in the diagram on the left that we have the lowest boiling points for alkanes at any length of carbons because they only have nonpolar London forces. Aldehydes, which have dipoles and London forces, are higher boiling. Alcohols, which have hydrogen bonding, dipoles, and London forces all together, are higher boiling still. Carboxylic acids have the highest boiling point overall because they have the same forces as alcohols, but their dipoles are much stronger. For the same reason, we see that carboxylic acids stay completely soluble for 1 carbon longer than the alcohols did. Alcohols were completely soluble up to 3 carbons. Carboxylic acids are till 4. They have more polar interactions on the carboxylic acids, and that can outweigh the growing carbon chain for just a little bit longer. We already know how to make carboxylic acids. They are the products of oxidations of aldehydes or strong oxidations of primary alcohols. So the reactions here aren't new. They're covered in 14a and in 15b. We have 2 types of reactions to carboxylic acids that are really important. The first is a simple acid-base reaction. Since the carboxylic acid is acidic, big surprise, any solution that is more basic is likely to remove a proton, another way of describing the H+ that is exchanged in most acid-base reactions. We say that the carboxylic acid is converted to its conjugate base form. Hopefully that's a familiar term from your Gen Chem. And in this case, it's a type of molecule called a carboxylate. For carboxylates, the threshold for a basic solution is actually pretty low. Anything above around 5 is likely to exist mostly as a carboxylate rather than as the carboxylic acid. Since neutral water is 7 and our blood is 7.4 for pH, We are far more likely to see carboxylic acids as carboxylates biologically. So whenever we have something that we'd consider a carboxylic acid, if we had it in our bodies, it would actually show up as a carboxylate in most cases. Most chemists and biologists learn to understand these two forms of a molecule as interchangeable depending on the pH. So they might use the acid name to refer to something that biologically is actually only in the basic form. For example, citric acid in the citric acid cycle is actually citrate. It's not actually the acid form. The citric acid cycle doesn't immediately ring a bell. It's the same as the Krebs cycle or the TCA cycle. Carboxylates are anions, so they typically are isolated with cations as an ionic compound. We call the carboxylate and the cation it's paired with a carboxylic acid salt or a carboxylate salt. This terminology doesn't matter much biologically since everything is dissolved in water anyway. So the cations and the carboxylate anions aren't paired. They're all free-flowing throughout the water solution of your body. In this course, we'll only worry about the carboxylate itself. Carboxylates are derived from carboxylic acids, as we just saw. And the easiest way to get their names is to think about the name of the carboxylic acid first, and then just change the ic acid part of the carboxylic acid name to ate. Think about changing carboxylate names this way, and it allows us to get to both IUPAC names and common names without learning a broader set of rules or a bunch of random additional trivial names. We have 4 molecules that we named earlier as acids that we can display the names of here. Now, this is the carboxylate, this is the anion form, but the acid was named butanoic acid in the top left, for example. When we decide to change that, we just switch out the ic acid, so like butanoic acid becomes butanoate. IUPAC names for acids are always oic acid, so the IUPAC carboxylates always will become O8. Hence butanoate, not just butanate. Pause and try to identify the other carboxylates. The top right, we have 2-methylpropanoic acid becoming 2-methylpropanoate in its basic form. Then we have 3-hydroxypropanoic acid, becoming 3-hydroxypropanoate in its basic form. And finally, 3-methoxypropanoic acid becoming 3-methoxypropanoate in its conjugate base form. This way of thinking works on common names too. So formic acid becomes formate, and benzoic acid becomes benzoate, as in sodium benzoate, a common food preservative. Benzoic acid is a common name that also is the official IUPAC name, and it's our only example here that ends in O8 since it starts in oic acid. The other molecules don't have that O, so they all end in ate. Try to name the last 2 carboxylate forms of the acids shown. Again, the acids are shown, but I want you to name the conjugate base of those acids. Carbonic acid is carbonate in basic form, and acetic acid is acetate in basic form.